Bismillahirrahmanirrahim. Good morning. Welcome at a new lecture. Today we will start and try to solve this question together. Like I said before, I depended on all my information on these two sources, solid state electric devices, and the second one, semiconductor physics and devices, basic principles. Okay, let's come back to our lecture to solve this question. Here we will dealing with silicon semiconductor material at room temperature. Is doped with arsenic atoms. Arsenic, like I said before, has 5 electrons at the last shell. We will attain to send one of them to can reach the stability situations and can build its wall with the other silicon atoms neighbors. Okay, here that's mean 2 point exponential 15, that's mean here equal ND, donor concentration at conduction band. And at the same time, doped with boron, like I said before, boron has 3 electrons at the last shell, that's mean will attain to take 1 electron from another silicon neighbors to can reach the stability and attained to take donor to take acceptor atom from the other. That's mean here 1.2 dot exponential 15 equal the concentration acceptor at the valence band. Question requirement A is the material N type or P type. From these two numbers, Na and Nd, and do comparison between them, we will see which of them will be the bigger one. Here, like we seeing here, 2 dot exponential 15 equal the donor concentration at the conduction band is the bigger one here. That's mean we dealing with N-type dots. We solve the number 1, determine requirement B, determine concentration of electrons and the concentration of holes. Let's solve that together. Here at the thermal equilibrium, maybe I forget it, right? That. Okay, we're dealing with thermal equilibrium, like the last question. Here we will using this equation. This will be the important one to us. Let me use the pencil here. Yes. Concentration of electrons at the B-type doped at thermal equilibrium here. Equal concentration of donor minus concentration of acceptor at valence band divided on 2 plus the same bracket but square plus intrinsic carrier concentration square. All these side will divided on half to force half, okay? Like we know, intrinsic carrier concentration, we calculated it before at the room temperature, Ni for silicon at room temperature equal 1.5 exponential 10, okay? Let's put all of these here. We have the result about Nd. Let me do that. Nd and Na, and like I said before, we know the result about Ni to silicon at room temperature. That means we can solve that. Here and note the number of electron concentration at thermal equilibrium equal A dot exponential 40. Okay, let me delete all of that. Come back to our mouse. Now to calculate, that's mean now we solved the result about concentration electron thermal equilibrium at the conduction band because we're dealing with N-type dot. Now to calculate the thermal equilibrium hole concentration in semiconductor, we will use the old equation, the mass law, Mass law, like we know, P naught concentration of electrons dot concentration of electron holes equal concentration carrier intrinsic carrier concentration square. Okay, we know the result about n naught because it is a dot exponential 14. That means we will do this simple math trick. P naught equal dot 281 exponential 16. Come back to mouse. Now, this is the important requirement here. Additional boron atoms are to be added such that the whole concentration. You mean what that's mean? That's mean here whole concentration, the new whole concentration. That's mean, let me write that here. Here, that's mean P naught dash. Okay, P naught dash. After that, what is the concentration of boron atoms must be added, and what is the new value of n naught? You mean what does mean? That's mean the new electron concentration. That's mean n naught dash. Okay. They solve it together. Additional boron atoms. That's mean here the not H. That's not right. We can write P naught dash. That's mean the new one. I know what that means. Let's try this. Okay. P naught dash. Okay. What concentration of boron atoms must be added, and what is the new value of a new electron concentration? Dash. I mean dash. Okay. Dash. The concentration of boron atoms, that's mean concentration of acceptor at the valence band by using this equation P naught dash, sure, equal Na, that's mean the new acceptor concentration at the valence band plus Na minus Nd, the donor concentration at the conduction band. Here, that's mean we can find the last result here about Na dash, the new acceptor concentration at the valence band equal 4.8 dot exponential 15. The new value of the new concentration, electrons at the valence band dash, at the conduction band, I mean, equal n naught dash P naught dash equal intrinsic carrier concentration by using this one. It's important, the same old equation, the same low mass, but with the new concentrations or concentrations and electron concentration. By that, easily we can find and calculate the last result to the n naught dash. I'm sorry because I forget it to put this. It's important to can do comparison easily between all of these results, because actually we can say we're using the same letters. When I put the prime, that will be easier to us. The concentration of the electron in the semiconductor, the last result is here, and not equal 0.562 exponential 5. Thank you about your watching. Thank you about your listening, your time. Görüşürüz arkadaşlar. Yeni derste görüşürüz inşallah. Kendinize çok iyi bakın. Let me stop the recording.